concepts and ideas, but my understanding from various aspects of it is rather limited. So my goal is to focus on the bigger picture, focus on the key concepts, and go through a few of the examples they gave, and conclude key points and lessons that could be learned from the paper. Just a tiny disclaimer, I'm using the latest version of the paper, which is by October 5th. I think the version that was linked on the course homepage was a little bit older. So regarding the content, this work is rather theoretical work. They do not have any empirical studies. Most of the things that they discuss is conceptual, but backed by some theory and derivations that they've done. The problem that they raise is that despite the fact that there are many objectives in representation learning and reinforcement learning, there hasn't been a clear way of relating these objectives to one another, and hasn't been any work before this one. So basically, they suggest that once we have such relationship, it is easier for us to also come up with new objective functions that are yet to be discovered. And so they provide a unified framework, which is based on KL divergence, minimization, and basically sees perception and action together and not as kind of isolated processes. In the end, they give a bunch of examples that lead to emergence of previously known objectives under the framework that they propose. Let's get a better understanding of the problem. So in ML task, we have 4 main pieces: data or environment in case of RL, the model, the objective function, and optimizer. The focus of this work is on objective function, but more specifically, the role of objective function in helping learning representations and basically taking actions in an environment. So it is tightly related to the model and data or the environment as well. However, I should also point out that the view that they have, it's not only limited to reinforcement learning, but the main purpose is to come up with a universal view that could help settings such as reinforcement learning settings where we have jointly like both kind of processes, both type of processes such as control or action taking, as well as perception. To elaborate a bit more, let's look at this diagram, which is showing an RL environment, including an agent and environment as main entities in this figure, interacting with one another, constructing a cycle in which the agent perceives the environment and quote-unquote thinks and takes actions which will influence the environment and consequently influencing the future perceptions of the agent as well. And this cycle goes on and on. As it is obvious and already briefly mentioned, the agent has 2 main processes running hand in hand. One is representation learning, which is basically the main, let's say, task in perception, as well as action or control. Now, there are dozens of algorithms out there that are already performing on a variety of tasks very well. This paper aims to look at these objective functions or objective functions that these algorithms came up with, and provide a universal framework that kind of relates how, for example, objective functions in one algorithm relates to another. And this is in the view of considering that we would like to do that considering both representation learning or perception process as well as the action process. So action perception divergence, or for short ADP, is looking at the objective functions when both of these processes are kind of considered in our view. This is results of the framework. So basically, what this framework achieves is that it relates different objectives, and different objectives emerge from this framework. And we are not going to go through each one of these objectives, but briefly mentioning a few of them. And basically, we are mostly trying to understand the framework that is proposed by this paper. So the framework is rather simple. It defines an objective as the KL divergence over the joint distribution of observable and latent variables x and z with a target distribution tau. Perhaps a simple example could a little bit clarify what each of these variables and notations mean. So consider a simple example of supervised learning on MNIST dataset. So X is a set of images that we have in the MNIST, and Z is the latent variable, kind of the blueprint for constructing each digit in the dataset. Maybe it's worth to kind of explain a little bit more what this latent or blueprint means. So in the MNIST, we have 10 digits. Let's say 1, 9, 8, 6, and some other. So now here, these are basically X's. Now the latent could be seen in this way, that the latent variable, which is kind of producing these digits, is 1, and there is another latent variable that is responsible for, or kind of explaining the other digits. So if you look, for example, what these digits have in common are kind of circular shapes in them, and maybe like some curves like this in case of 9 or 6. So basically, what I'm trying to kind of say here is that each of these digits could be seen as kind of like behind each of these digits could be seen a latent variable that is responsible for producing them. Of course, this latent variable does not exist in reality. What we observe are the digits, the x's, but considering a latent variable is kind of a way of thinking how we can model this problem. Okay, let's move on with other notations or terms in here. So the other thing that we have here is P, which is a joint distribution of the input data and the latent variables parameterized over phi. This could be thought as the network that we are basically training with parameters phi. And then we have the tau, which is also over the joint distribution of x's and z's. And this is basically a desired distribution that we would like to achieve. So we have an actual distribution, which is kind of materializes when we observe the samples in our data set, and it follows some stochastic process underlying it. at the same time, we are seeking for a target distribution or a desired distribution which explains kind of the relationship between the latent variable C and observations X or input data. Any questions so far? Anything that possibly could be confusing about these notations and what each of these variables mean?
Yeah, actually, sorry, can you hear me, please?
Yes, I can hear you.
Yeah, sorry.
No problem.
Can you hear me?
Yes, let me make some changes to my window so that I can
my question here is about phi.
Mm-hmm.
What, if you can explain it a little, like what does it mean?
I tried to explain it as an example in, for instance, the MNIST dataset, where we have basically a model which, I'm sorry, can you mute your microphone because I can hear you and yeah, it's confusing, thanks. So I was trying to kind of explain phi in an example, which in an MNIST dataset we would have, for example, a model, let's say a deep neural network that is modeling the joint distribution of the X and Z. So here the phi would be the parameters of the model that we are trying to optimize. Does that make sense? Okay, at the same time, maybe, or maybe you can tell me if there is anything confusing about this example. All right, so I hope that it was at least more or less clear, but if it was still like bothering you what phi means, maybe we can come back to it again later. Yeah, I was thinking maybe I can kind of think of a better example, but basically it is what it is. I'm not sure if I can explain it in any better way. All right, so let's go on. So in this basically way of formulating the problem, we are making some assumptions as well. Here we have two inductive biases that is existing in this formulation. One is the fact that the agent is optimizing an objective within which the random variables are also a way of representing uncertainty. So this is in itself kind of an inductive bias. And also the other one is that KL divergence is being used here as a measure of divergence. There are many other measures of divergence that could be employed. And this is just the one that is being used here. And this in itself is also another inductive bias. One clear reason for it is that if we use some other measure of divergence, other type of objectives will be produced as the result of using other divergences under the same conditions for the actual distribution and target distribution. We will be having a little bit of more examples and kind of information about this actual distribution and target distribution. Maybe by then things will be more clear about what each of these distributions are. But still, if you feel like my explanation were totally confusing, let me know so that I can try to at least explain it better in later slides. So with this, we come to also another fact about this, let's say, framework or formulation, which is about the generality of this formula. So as I said, using different measures would yield to different objectives. However, KL divergence is sufficient enough to basically explain the relationship between different objective, or at least familiar objective functions that we've had so far. Okay. This joint KL divergence could be written in different forms. One form is this latent preferences, which basically decomposes the KL divergence into two terms. And the first term is basically a regularizer to keep the belief over latent variables close to the marginal tau. And basically this term. And the second term, the first term in the second term is the variational bound. I'm sorry, the second term in general is the variational bound. And the first term within the second term is the term that basically maximizing it would look for latent variables that gives us more accurate results. And the second term within this information bound or variational bound is the term that when minimized, it gives more diverse inputs. So the same decomposition could be made, but this time instead of basically having a preference over latent variables, we would have a preference over the inputs. As you can see, for example, here the likelihood of observations given the latents is shown as opposed to likelihood of the latents given the observations. The same basically applies for the input preferences, basically regarding the meaning of each term. And the third kind of form that this scale divergence could be decomposed in is called the variational free energy, which is basically when the equation, the first equation, equation 3, have a constant value for its second term in the information bound. And this is true when we have inputs that are not changing with respect to the parameters, or we have a fixed data set. For example, in case of the MNIST data set, that is the case. For example, in reinforcement learning environment, that is not the case. And basically, the distribution, the actual distribution, the input data is changing with respect to the distribution of the data that we are modeling. The perception is affected in every step of the environment or the world. So this is basically reducing equation 3 to something called elbow or evidence lower bound. I'm just briefly going to explain this, what it is, as intuitive as possible. So when we have, let's say we have a probability distribution P, and this is not tractable distribution. We want to approximate, we want to basically estimate some basically value of how to put it, so we want to know what is the probability at the specific values out of this probability. So once it is not tractable, we need to approximate this probability distribution. So basically what we use is another probability distribution that is tractable, or we can basically calculate the values over this probability distribution and use this as kind of a proxy to this original probability distribution that we have. So there could be two cases. So basically, Q, the big capital Q, is representing the sets of all possible probability distributions that could be chosen as a proxy for the probability distribution P. If the family of Q basically our desired probability distribution, the one that we want to approximate, is within this family, then for sure we will find this. It is possible to find this, or in another sense, probability distribution Q would be equal to our desired probability distribution that we are trying to approximate. So not only we find it, not only it is an approximate, but actually it is the exact probability distribution that we are looking for. But in majority of the cases, this set Q, all possible distributions that could be a proxy for P, does not include this P star. So what will happen is that we go on some kind of search for the best possible Q. And this search is basically guided by calculating a kind of a divergence. Here it's a Kehl divergence. So we are seeking for a Q that has the least amount of divergence towards P star. And basically, this is what kind of variational approximation is. And since we are doing an approximation, we are finding a lower bound. So it is not exactly, so we know what's the kind of lower bound for this divergence, and we basically use this lower bound to find the optimal Q. I know it might be, my explanations might be a little bit chopped off or hard to understand, so please do jump in and ask questions. I do my best to answer them. So yeah, the point was that this divergence could be reduced down to this elbow, which is already known in variational inference and approximation. Okay, with this, we'll get to the models as preferences. I have to say, I'm also a little bit struggling about this, the concept of preferences, or what is the system configuration. But as far as my understanding goes, is that maybe let me go back to this slide. So basically, we can see it this way that, for example, the target distribution could be defined in many different ways. So let's say we have X, we have Z. So I'm drawing some graphical kind of model to show what are the possible way to represent this distribution. So basically, one way is, for example, to consider that the target distribution follows for example, such relationship. So this is one configuration. The other configuration is this, and many other possibilities that exist. We can also parameterize this relationship. For example, say that this relationship is parameterized by theta. My understanding is that when you say parameterizing this relationship, it means that you are defining a parametric model in order to define this relationship. For example, you define a neural network that basically approximates this relationship. So maybe that also helps. I don't know who asked the question regarding the parameter phi, but maybe this helps. So basically, we have different configurations for system, and system here is being like this whole system. It constitutes of different parts, and basically different parts could take different configurations. And for example, in one configuration, we have, for example, here we have, well, this was over tau, so maybe. So here we have such relationship. Here we have such relationship. Yes, and this is like preference on the latent variable. This one is preference on the input. I think this is just some jargon to terminology to basically convey these concepts, but I could be slightly wrong. This is based on my intuition. I'm not sure if it totally makes sense to you or not, but I hope it does. If someone else has some better explanation, please again jump in. So again, let's go back to where we left off. So models as preference. Again, here I guess the preference means that treating model in some particular manner. And this particular manner is basically considering that target distribution could be treated, for example, as a probabilistic model. So we put some preference over how the model should look like, or in other words, target distribution should look like. One point that they make is that this minimizing the joint divergence, basically the KL divergence that we saw in the previous slide, is also minimizing the distribution over the input data, as well as the distribution of the input data under the model. So basically this model, or tau x, is kind of an ideal thing that we would like to achieve. It's something that we would like to kind of estimate with this other distribution or actual distribution. This itself, it could also be parameterized and kind of being estimated as part of our training or learning process, but it could also remain unparameterized. It could be some, for example, a heuristic that we are learning something based on. So another point that they make about the different aspects of this APD, or minimizing the joint divergence, or this framework, is that there are, like, the action perception cycle that exists is basically aligned with the idea of perception as inference. So there is this kind of way of kind of formulating the problem as perception as inference. It is aligned with that, and also it basically has the same interpretations that active inference has. I'll try to also a little bit elaborate about active inference, but briefly for now, it's different. You can think of it as a different framework compared to this divergence minimization that they propose. But the interpretations on the action perception cycle is basically the same as in active inference. Before talking about niche seeking, this figure basically explains this action perception cycle. Essentially, we have sets of inputs that are perception or representation or belief of the world is constructed based on. And based on our belief, we take actions which basically influences the world. So one is, like, each of them are aiming, although they're basically minimizing the same target. So both of these, perception and action, they're minimizing the same target, but they're influencing different variables in this system. One is trying to align its belief with the world based on the inputs. The other one is trying to change the world based on its belief. The first one was perception, the second one was action. So this is the view that exists in active inference, as well as the divergence minimization that they formulate. The same thing that I just said now could be much easier kind of be seen in a graphical depiction of this concept. So basically, we have past, and we have the future, and we have the latent variables. The whole system is trying to minimize for this target. We would like to achieve our kind of idealistic or desired model of the world, because we want to be able to operate very well in the world. But the perception process is basically receiving, basically perceiving the world, and it updates its belief, while the action is basically using the beliefs in order to change the world, to align the world with its belief. And this goes hand in hand as long as the world is kind of progressing, and we get from past to future. So it's basically kind of another way of depicting the concept and saying the same thing about the action perception cycle. Now, about niche seeking. So what we would like to be able to do, this is also one possible configuration out of many for the target distribution. But I would say this is more like a general view or a very widely seen view over the world or the way that we would like to model our world. So basically, the target distribution is defined as such that the latent variable is explaining the past while it is predicting the future. And there could be also, and what kind of connects the past to the future is basically how, like, a specific, let's say, order of observations is valued, and how this value kind of shows itself, or yeah, basically manifests itself into the future. For example, if you see that the weather is bad and pandemic is getting like worse, for example, as the past history or current observations, then this kind of gives, let's say, low reward, or like kind of unfortunate prospect for the future. So if you want kind of to value what future states would be based on the current observations. But I have to admit, I also have a little bit of difficulty understanding the concept around this reward thing. But back to the niche seeking, the point is that as more expressive model as we have, the more flexibility we have, and more flexibility we have, the better chances we have to be able to minimize this divergence. And once you're able to minimize this divergence, basically you're finding some ecological niches in the environment, which basically predicts the input data very well. Yeah, that's all about the model's preferences. So here there is a comparison between different, let's say, frameworks. So unfortunately, I don't have like sufficient idea about this expected reward, why it does not have this latent entropy and input entropy. But my kind of intuitive understanding is that because receiving the rewards, it's not related to the entropy of the input data, nor the entropy of the latent variable. Or like pure entropy, we could kind of see it as the rich fullness of like information, like how much information the latent or the input provides. I'm going to skip this maybe for now, and later maybe we can discuss it further. But the gist of this part is basically that the joint divergence minimization is basically yielding to a representation that is informative of the past input, and also enable us to explore the future inputs that are informative of the representation. So I think this is like the center point of the paper, and kind of the philosophical point of the paper that this framework is basically constructed based on. Any ideas or any inputs so far? If not, I'm going to continue. So an important thing that this paper is doing, like basically the important step in this framework, is the way that they split the information bound. So they split the information bound into a term that explains the past, a term that explains the future. Just for the reference, I put these diagrams as well, because this is kind of motivated by these diagrams. In an illustrative way, if you want to think, since you have basically the past, the future, and they basically interact with your latent variable, and basically there are two different processes, you would also like to consider these as separate terms in your framework so that basically make your objective a bit more interpretable and make some kind of intuitive understanding of, okay, what are these terms, how they interact with each other within the objective function. So maybe briefly, if you look at the first term, this is supposed to be telling us something about the future. It's called the future information bound, but maybe just at the first look, we cannot see anything, and it is also conditioned on the past. So how is it that it's called the future information bound? I think it is for the same fact that we know that this latent variables basically are the ones that enables us to make actions, and that is, actions are supposed to influence the future. That is why this is called the future information bound. And the other one is, I think, for the most part, clear. So basically, this decomposition into the past and future provides us this more comprehensive decomposition. So basically, after splitting the information bound into past and future terms, plugging it into the divergence minimization, or the scale divergence that was introduced, then this one kind of gives to these four terms. As an example of past and future inputs, maybe it is good, it gives a more kind of practical idea of what does these past inputs and future inputs mean in practice. So past inputs could be thought of the experiences that are stored in the data set. For example, you run an agent in an environment, and this agent gathers some information, and basically you put them stored into a data set and basically use these previous experiences. Like in the case of autonomous car, for example, you run the autonomous car over different conditions, different seasons, and basically you gather all this data and basically use it as some history that basically is essential to construct an autonomous car based on. And the future inputs could be basically the learned world model, or kind of a pre-trained model, or on policy trajectories, which means that as you are constructing the future, you're also kind of altering your policies, or it could be a kind of replay of past input. So you can store all this data that you gathered for your autonomous car, for instance, and then you basically replay it as if you're running a simulation for an agent. So this could be thought of as the future inputs, just to give you some perspective of what these past and future inputs could look like.
Excuse me, I have a question here.
Yeah, sure.
As I understand, like when in the joint divergence, when they try to split the information bound to two parts, and I think in the second line they consider it. I think the target distribution is always bigger than the actual distribution. That's why. So it's always we have something like the target distribution is bigger than or less. No, they consider it the opposite. I think the actual distribution is bigger than target distribution. So we have tau, it's smaller here. So, and we have it like always, it's like that. So my question, like why it's smaller, or why we consider it smaller like tau?
I think there was a clear explanation for this in the paper, but I don't have it top of my head. But I can kind of think about it logically and see what I can make out of it. So,
Okay.
The first line is basically, so the only difference in these two lines are this term, which is the likelihood of the latent variables under the past history. And in the second line, we have the distribution replaced with the target distribution, or model distribution. And what we are saying is that the information bound is always bigger than this second line. So I'm not sure if the information bound had to be. I think the information bound had to be increased, but it doesn't make sense. So I think in this context, the information bound has to be reduced, minimized. In that sense, if we assume it is the case, although I'm not sure, then it means that we are not able to minimize it more than we can minimize it with the desired target distribution. I think this is what I would make out of it, but that's just, let's say, a conjecture. We have to look at the paper, the part that they were explaining about this. So your question was that why it is bigger and equal, right?
Yeah, actually, when I was looking at the paper, yeah, they put some assumption, I think, about this, which is they assume, I think, the actual distribution is kind of bigger than the target, and without explanation why, and something maybe it's trivial or obvious things, but at least, yeah, I think it's not. I don't know why, like they assume it's something like that.
Maybe let's just look at only this term. So this term is the likelihood of the latents while we have observed the history of input data. So basically our aim is to maximize this likelihood, because as higher the likelihood it is, basically the more informative the latent variables are regarding the history that we've seen. So in a sense, we would be able to explain better the history, we would be able to predict the future better. Now, the reality is that so I think it would make sense to say that the actual distribution, basically the likelihood of this term is not gonna get bigger than this term. because this is like kind of the desired, kind of the idealistic kind of reality that we can have, although it doesn't come to reality. But I think the fact that, so this should actually be smaller and equal if we were only looking at these two terms. But I think there are some other like interactions between these terms that turns this into bigger and equal. But in a kind of looking in a micro kind of terms, this is what I would make out of it. But I can check again at the end and basically discuss it while we're doing the test or discussing some other matters. But thanks for bringing this up. Let me write it somewhere, not to forget it. Okay, so let's maybe try to look at this decomposition and try to intuitively understand which term means what. So basically we have this same Kale divergence that we had, now decomposed in some terms. So the first two terms, like this term, these two terms, correspond to the past, while these two terms correspond to the future. Now, the first term is basically trying to keep the belief that we have, or the likelihood of latent variables given the history. Another way to refer to this probability is basically calling it belief. So the goal is, in this first term, is to keep the belief as close as possible to the prior that we have for latent variables, which is defined by the target. So this is kind of a inductive bias for the belief that we have over the latent variables. It keeps it within some reasonable, let's say, bounds that is defined by this inductive bias, that is prior that we have. The second term is basically aligning the past, aligning the belief with the past. I think it could be called as the reconstruction loss. And this other term within this representation learning is basically fixed for a constant for the same reason that we had before, because the input data in the past is not changing with respect to the parameters of our distribution phi. This third term, although it is mentioned as control objective, but I call it the steering limit, and I will explain it in a bit why. So this is basically the preferred input distribution, which is basically aligning the world with the belief. So if you look, we have the future given the past and the latent variables. And basically we are shaping the future using the past and the latent variable. And latent variable is something that the agent is in charge of and control of. And basically we are trying to make this likelihood as close as possible, or beliefs over the future, or kind of our prediction about the future as close as possible to a dynamic that we are aware of, which we know that, for example, how the future should be look like given the past. And in a sense, it's called control objective in the paper, and it makes sense because it's kind of controlling the, let's say, trajectories of the agent into the future. But they call it the steering limit because this is more actually like a regularization for how the future should be looking like. And this becomes more clear in a second when I explain this last term. So I would call this one the control objective because basically this is kind of explaining that the future inputs are going to be informative of the latent. So this X is basically the past and the future, and basically we are trying to shape the belief, shape the latent variable such that the whole history and the future is also considered. So obviously, the better the latent variables you would have, you're exploring also more, let's say, efficiently finding the niches in the environment. So this is basically more, I would say, a term that is more influential in terms of controlling, but then we have some dynamics that we would like to consider, like kind of, we have some limits. We want to steer our controlling wheel, and we do not want it to basically go out of whack. So it's like this term, this first term is more like a regularization for this exploration. And yeah, so saying that is actually kind of these two terms are the main terms for basically this one is recreating the history or the past as good as possible with the highest possible accuracy. This one is basically helping the agent to basically explore the future. At the same time, we are regularizing each of these two terms with some bounds, like basically having a prior bias, which is regularizing the reconstruction, and having a steering limit, as I would put it, that would bound the control objective or our exploration. Although this is something that I made it up, so it could be misleading or not really the right way to put it, but this is basically based on my understanding. I think it makes sense, unless someone has some counter example or counter argument about this. Okay, any point so far about this part? If not, let's continue. So basically, the objective that you saw in the previous slide enables us to derive different objectives, as you can see in this table, and basically authors in this paper do so, and basically look at different algorithms for agents, which have different sorts of objectives, and they put it into the framework that they developed. And so the main parts of the framework includes like latent variables, the target, what is the latent, what is the target, and then they, as you saw in the previous slides, they have this decomposition into the past term and future term. So basically they derive these objectives within the framework of their own, and then they basically mention what the future term, for example, means in these agents. For example, here it doesn't have a past term. So basically characterizing these the objective of these agents within the framework that they developed. So we are not going to look at the derivation or trying to dig deeper into this, just kind of staying at the bigger picture here. Saying that, this is also another view over the familiar objectives existing in the literature that basically they were able to recover from their framework. So basically, using their framework, you can basically plug in your assumptions about the latent variables and the target distribution and the actual distribution, and basically recover each one of these objectives that they show here. And they categorize it basically into three categories. One is perception, which is basically the case where the latent representations are not controllable. I'm sorry, the case where the latent representations like there exists some latent representation, but without any controllable input. And the other case, which is the case of action, they have some controllable input, but without any latent representation. And the last case, which is including both of these kind of cases included, is the information gain, where you have the good of both folds. Yeah. So this being said, we get to examples of the paper. So basically, in the examples, they kind of derive and recover all these objectives that you saw in the figure. Here, I'm just going to go through one example and mention the information gain, which is kind of the fruit of the paper. So I chose the amortized inference because I thought that it's the one that is most familiar to everyone. It is basically the case of a variational autoencoder. And if you look basically in the actual P, you can see the encoder, and the target tau, you can see the decoder. So as I mentioned, it is possible to keep the tau unparameterized, or here that is parameterized. So it's basically part of the target itself is part of the model to learn and optimize. And basically, we have these assumptions for the case of amortized inference, or you can think of it for the case of the VAE, variational autoencoder. And basically, you can write the probability, the joint probability of X and Z under each of these distributions shown in these graphs as such. And basically plugging in this and having these assumptions, you can recover from the framework, the K divergence in the framework, the more summarized terms. And this is basically yields to the elbow. And we know from the variational autoencoder that it is actually optimizing the elbow.
Actually, here in this example, it's clear, like the target is smaller, should be than the actual P, but the original formula, like if you want to use it to different kind of examples, I don't know if it works with variation autoencoder. Yeah, it's obvious, like we need distribution, which is kind of smaller or somehow or compressed version of the original data what we have. That's why it was in the formula considered like that. But different examples, like I don't know if it's our target. It's like that, but we need it all the time like that, similar to the idea about variation of encoder.
Yeah, thanks for bringing this up again. Actually, I think this example kind of explains it very well. It's more intuitive to think of it in the context of this example. So just kind of repeat in more words what Modar mentioned. So basically, what he said, you can correct me if I'm wrong. So basically, in a variational autoencoder, what we are doing is that this is the encoder and this is the decoder. So we have the X, and we are kind of reconstructing the input data. So what it means, like, or how to see the previous term, why it was bigger and equal, is as simple as this, to think of it that we are compressing some data into some limited number of variables, latent variables Z. And there we are trying to recover the same, like, original data from the input space, basically by X tilde. Now, what was that term was saying? It was basically an expectation over the divergence of something. So basically, if this is the target, this is the actual distribution, then that term was saying that, like, abusing the notation a bit, but I think it's something important that it gives the message. So it was saying that so the divergence of this recovery, this decoding, is going to be bigger than encoding. And it makes sense because you're losing some amount of information. So this, like, kind of the distance of what you create, in a sense, the distance of the samples that you recreate is not going to be kind of less than of what the, like, under, let's say, under distribution. Under distribution P we would have. So this is the way I would understand it. Maybe Modar, you can also kind of elaborate more, say if this was what you were thinking about, or you were actually saying something else.
Yeah, it was a good, very good explanation, and yeah, I could, like, if we use different examples, like, we can understand the framework in a better way. There is lots of examples in this paper, like, to cover, and everyone somehow different.
Unfortunately, or maybe fortunately, I didn't go down the path to derive these because first I couldn't see myself that I can pull it off, because it's like, yeah, there was first of all too much of information kind of compressed into this paper, as well as like deriving, it could become nasty and it make people even more confused. But certainly the right way to go with it is to actually derive all of these and to see if you can get both the intuition and the correct mathematical understanding. Sadly, I couldn't make it in this presentation, but it could be a session for future seminars or efforts.
Yeah, but that general idea or about framework, it's already explained. So I think there will be, like, infinity number of examples somehow, like, to apply maybe such framework, and one use it yet. But yeah, the main idea about it, or the framework, is the most important thing which you explain it already. Explain it for us. Yeah, and it was interesting how everything like related to KL divergence it's applied in different places. So for me, first time I read how they use KL divergence in this scenario.
Yeah, it's definitely a good practice to see all of this together. Also, this work is basically a kind of literature review linking works from many decades ago so far till to this day. So yeah, but thank you very much for your input. Appreciate it. So let's maybe continue almost at the end. So another example that I would like to kind of emphasis on is the last example that they have, which is the mutual information, about the mutual information, which considers both perception and action both together. And basically, I think it is kind of the gist of the paper in terms of what is the right or good objective to have. Basically, as far as I understood, it is what authors implicate, or even points explicitly mention that it's the most universal objective to be learned, at least in the context of RL, because it's jointly considering both perception and action within the objective, which means that we have a directive for our model to be optimized, taking into account both processes at the same time. And basically, some examples of such objective is Bayesian DQN, or if you're familiar with SLAM, simultaneous localization and mapping, it also considers the mutual information. I actually forgot to include some examples of maybe what are the models on the right, on the action side, that are not using any latent representation. And the ones that I could think of, I'm not sure if the paper had mentioned this, but since I had the history working with such models, I thought it might also be useful to some of you to kind of relate it to your past experience if you've worked with such models. So basically, the controlling models, or models that are specifically are made for making actions, but without any latent representation or representation learning, or, for example, Kalman filter, or basically, I think all classical control systems like PID controllers and such. So they do not have really a latent representation of the history or the future that they would like to predict, but they're somehow putting together a system that is not reliant on latent representation, but it's enabled to control the system. So basically, this was it from the examples, although I wanted to perhaps go more into the examples and go through other examples as well. But one problem was that there were so many related topics to the reinforcement learning that is also not my area, and so many new concepts like empowerment or skill recovery, things like this, that would make the presentation complicated. So that was one reason why I avoided it, but still it doesn't mean that we cannot talk about it. And, I more or less read those parts as well, so we can discuss things if you have certain questions to talk about those parts. So with this, we get to the related works that the authors talked about. They've mentioned that regarding the divergence minimization, there has been no work that considers the representation learning and the control aspects. Also, one thing that they've done I haven't discussed it much. We can also discuss it further. If you have a question about it, is that they are optimizing the backward KL as opposed to forward KL. So apparently there are some works that basically more or less doing the same, but with the forward KL. Also regarding the active inference, since the framework was related tightly to this concept, as it was mentioned, they mentioned that kind of as related work that this APD is inheriting interpretations from the active inference, and, but the main difference with active inference is that in active inference, we are maximizing the probability of the input under the model, while divergence minimization is matching the input distribution under the model. So more or less both are aiming for the same thing, but they are doing it in two different ways that has different consequences. The main consequences that I didn't really delve deeper into was about the niche seeking and which one is more capable of finding niche seeking. But roughly speaking, divergence minimization is more robust and does not kind of converge to the trivial examples. This I also kind of postponed it to the post-discussion of the presentation. So if you had some questions, we can discuss it. And one more thing about the active inference is that they mentioned that active inference is more costly computationally due to some properties that active inference is inherited from certain methods like variational inference. And lastly, it's about the control as inference. Basically, the aspects related to the control mentioned in the divergence minimization framework is not that new, but the aspect that made this work novelty, basically the novelty that they added was that they made the control as inference consistent over time. I'm not quite sure about how this is done, but it has to do with this exploration term that they had used, and that was emerged as a result of splitting it into the past and future. So last but not least, the conclusions. So basically, the authors introduced a unified objective for action and perception, more like a unified framework for objective. And one important aspect of it was that it was consistent with the objective over time. As I said, we did not discuss this into the details. The other thing that the authors did was that they provided an understanding over the latent variables, how they influence decision making, and basically this was discussed in the examples, and as a result, the information gain was kind of the fruit of this study about the latent variables. The other kind of thing that this work brings to the community is that it enables more adaptive agents. And this is basically possible through expressive word models. They argue that if you use the target models for the target distribution that are expressive enough, let's say deep neural network, because they're very flexible, then it enables you to achieve as good as the divergence minimization can get you. So, so if you want to have better agents, more adaptable agents with different environments, you need to have an expressive model. However, they make some kind of claims that this needs to be kind of proved. So it was just mentioned as a kind of an intuitive way of saying it in this paper. They did not actually prove or support it with experimental data or experimental studies. And the other aspect of this work was that they provided a general recipe. So basically the framework is not only providing kind of the best way of taking into account different procedures such as perception and action, but also providing a recipe how to derive new objective functions. And with that, last but not least, they also gave a hint about how new families of objective functions could be produced as a result of using this framework, as well as considering different divergence measures. So the last word is my take from this paper. So this paper was basically a universal view also on the literature review, and basically it was a literature review kind of, as it included lots of links and how this framework basically explains every piece of work that is done in the literature regarding the presentation learning and control in both of the communities. And kind of it could be seen that there are two pathways in the deep learning and machine learning community. One is particularly focused on architectures, and the other one is kind of related to objective function, but I don't know if there is any better word to use. But as you can see, this whole paper is about objective functions, but it has implications on representation, on action, on expressiveness of the models, which also could imply the architecture choices. So I think a new word could be found for this to explain it better, but basically objective function, I think, is the right way to tag this kind of track within the community. And of course, there is always application aspects that are important, but that's the way I wanted to kind of look at the community. This paper wasn't mathematically very challenging, but conceptually is heavy. So I really encourage to look at the background information, and the good thing about it is that it's kind of a universal knowledge. If you understand these concepts, it's not just giving some skills for a particular field in deep learning. I guess it stretches across all areas of deep learning. I know, like reinforcement learning, supervised learning, online learning, active learning, all different types. Doesn't matter what area you're working on. But of course, the concepts are a little bit heavy, and there are lots of links and jargon that needs to be tackled. So still a lot to digest. I think the most important aspect of the paper was the examples. I'm sad that I could not make those parts, elaborate more on those parts. We can discuss it. And the other thing that I think is very important is that this paper, along some other papers, again, kind of proved to myself that the variational methods and latent variable methods are really important, and there are some fundamental concepts actually that need to be learned, I think anyone who's working in machine learning. So there are some related topics such as measure theory and information theory and Bayesian methods that are related to this. So I really hope that our curriculum would get more and more of those aspects into it, because despite the fact that it's crucial and it's like kind of showing up in every piece of literature, still I think it is not as much appreciated in the university teaching and curriculum. And this is kind of a future work for myself, but I think it's really nice to try the derivations. And the one exciting aspect of this paper is that it explicitly calls out for some future work, and future works are not some twisted, difficult things to perhaps find out. It's just one thing that could be done is to take another measure of probability measure like the Wasserstein distance and basically derive the same things for the Wasserstein distance and see what it recovers and how it compares with this current framework. So that's really an exciting thing for those who are interested. Perhaps those who are interested could have a chat with me. I would like to make some, initiate something in this, perhaps for myself. If there were people who were interested, it would be good to do it together. And last but not least, the work was very elegant, but yet intimidating work. 20 so pages. It had 7 pages of only references. That's quite astonishing, I guess. It was linking all pieces of work in the literature. At the same time, it was done by a PhD student at the University of Toronto, which is kind of raising the bar, I guess, for the PhD students. I myself, so encouraging but intimidating at the same time. All in all, I hope that you liked the presentation, and now we can go to the questions and discussions. Thank you.
Thank you for the presentation, Owen.
No problem. I hope we can clarify some points now.
Sorry?
I hope we can clarify those points that I was not quite clear right now.
Actually, like it's we're like looking at some formula which is not very clear, but we already discussed some of them during the presentation, and the idea about splitting the information bound into like future and past, which is what something nice they did for this variational bound. And you know, like and you explain it, I think, like using some small graph. What the reason, like they try to split this variation about information, matching information to two sides, like to two parts, the past and future. And about this paper, like as I understand, like it's kind of a new approach to study the perception and action in a joint scenario, joined together, because usually it was like perception and action study in isolation, as I understand, like most of the time. Do you think like this approach is helpful to continue with, for example?
Sorry, can you repeat your last question? Do I think these approaches are what?
My question is like, do you think this approach, joint approach, it's described now, is it helpful to study the perception and action? Because it's usually these kind of concepts are studied separately, as I know.
Yeah, good point. Actually, I was trying to kind of think about this when they say that perception and action are studied in isolation, or kind of the link between these two within the objective functions are not considered in the previous works. What does it mean? So what I concluded for myself was that it doesn't mean that they are independently kind of, let's say if someone came up with an objective function, it doesn't mean that they drive it independently for perception and action. It could literally be that I'm aware of like systems, for example, robotic systems that they have different world model than they have a control mechanism for the behavior of the robot. Basically, there are two separate algorithms. For example, a Kalman filter for the localization of the robot. At the same time, they have like a separate, let's say, automata which controls the behavior of the robot. And they're basically not like literally the objective functions for each of the like these two separate procedures are like different and separate and do not really interact. But in case of reinforcement learning, like the agents that we have, for example, in common environments, like in OpenAI, I don't know, any of these environments, like the models that we have, like the QN and such, basically, like with the emergence of the deep learning, we have models that are encapsulating both the representation learning, the perception aspects, as well as the policy making or action taking or control within the same model. They're literally like coexisting within the parameters of the network. And if there is such objective function, for example, to train a DQN that enables the agent to operate in an environment successfully and gathers as much rewards, and we can call it successful agent, more or less. And it means that this objective function has considered both aspects of representation learning and action. And literally, let's say, the way that these two manifest themselves, like these, like perception and action, they actually like physically exist within same sets of parameters. So I think in that sense, it doesn't mean that currently existing objective functions, or at least not all of them, it doesn't mean that they are looking at perception and action literally in separate ways. But it means that they're not also making an attempt to, for example, give an interpretation over different terms within the objective function, over what it means, for example, for the perception procedures. What does it mean, for example, this term for the control or action? So what this framework does is not that it is introducing some revolutionary, let's say, I would say it's not like a revolutionary thing that would change the arena of, let's say, objective functions. What they've done is basically they observe what type of objective functions was created in the literature. And then they try to see if it could be framed under the same kind of framework, and basically view all of these objective functions under the same kind of discipline or disciplinary way. And then basically they recovered these relationships. They found out, okay, actually the amortized inference is tightly related to the variational inference, but in this way, if such term kind of cancels out because of this assumption, it yields to amortized inference, and so on and so forth. So for the rest of this, basically, figure one that they provided in the paper. But nonetheless, I think it is an important step. It's more like you have Newtonian physics, you have, I don't know, particle physics, you have astrophysicists working on different formulas, and basically someone comes in and basically finds out the relationship. For example, says that, okay, when an object moves higher than the speed of light, then the Newtonian laws change into kind of the formula that Einstein came up with. So basically, it's like kind of explaining, like providing a bigger picture for the whole effort that was being made before that. So it's a considerable thing. It could be revolutionary. I think at this point it's not like some, perhaps, I don't know, that's my gut feeling. It's not quite a surprise, let's say. It was just a very wise observation, and they put it together in such elegant way, I would say. But thanks for this question. I hope it was clear. And does that make sense to you?
Yeah, sure. Yeah. Thank you.
I have a question. We don't have much time, so if anyone needs to leave, then leave. But so my question is, so I always have a problem with Carl's present framework. So he's one of the authors, and he's the advocate for this free energy principle, which leads to active inference and also to this framework. So how I understand it usually is some sort of imagine, or you are a robot and you imagine that you have a box in front of you. And actually there is no box, right? So now you have two options. So either you change your belief of the world, or either you do something in the world so the box is in front of you, right? Mm-hmm. And so in this, so they propose this equation 6, where they split all these possibilities, at least these two possibilities, and I believe probably more. But anyways, they have this exploration term, right? Or empowerment, or as you call it, control objective. Mm-hmm. So how do they balance this? So I have these two options, right? So it's up to me to choose what option to go for. And here is, again, you can explore or you can exploit, right? And I don't see the way they balance this. Yeah, I don't know if you have any intuition or they explain it somewhere on how this exploration is actually balanced, because this is minimizing something, but what's the end result like?
Mm-hmm. Actually, I've seen a part in the paper that explains this and why this is actually kind of superior to any other way of doing it. So basically, as far as I understood, this exploration term enables the agent to explore without like additional, let's say, without reward actually in the environment. So you're basically setting the agent in the environment, and agent is enabled to explore and find niches in the environment that is essential for surviving in that environment. So it's like has some hints at least to what ideal we have in mind about intelligent agents and general artificial intelligence. But as far as it goes to my intuition or understanding how this actually works, I think I need to look at the paper again and say, because yeah, top of my head, I think I don't have anything to add to this. But this term is also very similar to the information bound that they provide in the background information. And there's some really crucial points mentioned there that helps in understanding of this term and the rest of the terms in this relation. But what I can add right now is that even though this control objective or this exploration term provides, despite the fact this is supposed to provide like a universal way of agents exploring the environment, I think it is still doomed to failure, because anyway, we need to regularize one way or the other. The way that we're regularizing here, for example, if you look at the steering term, basically, whatever exploration you're doing is kind of bound to what we experienced before and what we are possibly going to experience in the future. And our prediction of the future is also relying on the history, nothing more than that. I mean, this would lead to some extraordinary results if we had like somehow some oracle here, like some god that could foresee or gives us some hint about the future. Then it would make it like something, but this is obviously nothing that would happen in the reality. So, which means that, for example, let's say you had an agent, an intelligent system that was living on Earth with a gravity of 9.8 for thousands of years, and then all of a sudden the gravity goes to 5, and basically the laws of physics that this agent was trained on changed dramatically all of a sudden. So, since it was not trained to see such case, of course, it's not going to react like intelligently or in a smart way, and it would be doomed to failure. But of course, this exploration term is going to help us help it out to explore and find out what is the right law under the new gravitational force. But now consider a case that is like, this was like a tiny change in one dimension of the environment. Now consider that there is more dramatic change. I don't know. I cannot think of a more dramatic change. But consider there was some very dramatic change. Then that would basically ruins all of our assumptions and the latent representation that the agent was made to that point. Then this exploration is, of course, irrelevant, because anyway, the regularization term that we have and the inductive bias and assumptions basically that we make about the world is totally incorrect. So at the end of the story, I guess you're all doomed to the restriction of our assumptions about the environment. There should be some assumptions, otherwise we cannot, at least in like these probabilistic frameworks or Bayesian frameworks, there should be some assumption, and if there is no assumption, there is less chance of getting like something useful out of it. And obviously, the only way to make some assumptions and create some inductive biases, like a frequentist approach. Basically, you sample and sample from the environment and live in an environment for long enough to learn some basic patterns and basically incorporate those patterns within your system. So even the Bayesian methods, they're kind of like using the idea of frequentism or frequentist methods. The only difference is that they come up with a prior that is most probably calculated with a frequentist way. So, but yeah, I think I have to check maybe more. I would be more than happy to check it again, this exploration, see what I can make out of it, and we can continue to chat on Slack about this. Oriel, I hope that what I explained was at least more or less relevant to what you asked.
I don't think there is an answer. Like at the end, these frameworks are very abstract yet. There is no clear, at least to me, implementation of it. So I guess it depends on the implementation, how these things are dealt with.
I think actually not. This is not the case, because basically we already have examples of this framework, at least in this framework in particular. So basically, any of these methods, I don't know, A3C, SQL, SAC, V, all of them are basically interpretable within this framework. Now, some of them are kind of preferred based on the argument this paper has been making. For example, among these, I reckon that we would like our future term to be information gain. But of course, this is like, this could be different case by case, but still, it seems information gain is like a more universal way of looking at the problem. At the same time, yeah, so there are, of course, some differences in the way that each of these methods are operating based on the past theorem. Basically, these terms, I think, to some level introduce the inductive bias and the type of regularization. But the methods exist, they are there, and this framework is, if anything, this framework is actually providing a recipe how to come up with new objective functions. So it's possible that we can actually now come up with a better, more universal objective function that is explained by this framework.
Yeah, in these frameworks, this balance between exploration and exploitation is very hard-coded in the sense that every method probably, or at least I know at least 2 or 3 of them, that they have very different balance, or how they balance this exploration exploitation, which is not, at least I don't see how it relates to the formula they give, like action entropy, at least in A3C and these things, or even empowerment. At the end is some weight that you just predefined or maybe even learn, but in the framework they don't seem to give a recipe on how to balance this.
Yeah, that's definitely the case. I would actually associate this it's not a problem of a framework, and I think there is no such framework existing. This is more like a philosophical concept of like no free lunch theory. So if you have, I don't know, better exploration, you use your exploitation. If you have better exploitation, you lose your exploration, and all these like kind of trade-offs. It's like there's some kind of the dimensions or which we would like to optimize our things is like kind of perpendicular. So if you take on one path, you cannot go on the others. So I think it's a fault of not a fault of the framework, and most probably there will be no universal framework that would answer it all. And we would always have these issues. We have to choose, prioritize one thing over the other. I think that's also one thing that this framework actually is telling us, in a sense. Okay, great discussion. Thank you very much from everyone.
Yeah, maybe just I need to add maybe last thing, like
yeah, sure.
maybe for yeah, as I could see here, the goal is to find phi, for example, to optimize this like to find the closest distribution. And if you need to think about it in an abstract way somehow, I think like the goal, like it was in this paper, like to have this kind of work on perception and action, to have this work together, or somehow, I don't know, like not which was studied in isolation to be one of them, but I think the formula or something, this idea, it's very powerful, and but it has also, if you couldn't find very good phi for this, in practice, it's more dangerous, like to work on such idea. Yeah, even they mentioned like perception and action study in isolation, because if you are trying to use such idea for joint approach, it's good and it's more powerful, but at the same time it's dangerous about like finding phi. I don't think it's in practice or something like that, like kind of minimization problem. It's easy.
Yeah, actually, like continue to your words. What I'm actually really looking forward to is like the empirical studies on these like examples, because no matter how much like you work on the theory, but there are always aspects that you haven't seen, and it actually comes out of the empirical study. So I think there will be so many insights also after these ideas are being validated using data and some experiments. But the framework is already sound, and it seems to be legit. And as it is explaining so many different already existing agents and algorithms made for the reinforcement learning. So I would expect that more or less the empirical studies should align with the theory, at least for the most part. Those parts that are not going to be aligned most probably going to be very interesting to see what it is if it's not going to be aligned.
Yes, thank you for the presentation again. It was so nice.
Sorry, come again? I couldn't hear.
Yeah, I'm telling you, it was so nice presentation. Thank you.
No problem. I hope that at least it gives some new knowledge to everyone. And thank you very much for your attention. We'd be more than happy to continue the discussion over Slack, or if you wanted to chat about, we can always meet in person. We'd be more than happy to discuss this stuff.
Okay.
If there is any question about the test, I can answer. Unfortunately, I didn't put hints or explaining the answers, but I can elaborate on any answers if need be. All right. If not, then thank you very much.
Thanks. See you next week. Bye.
See you. Bye.
You are currently the only person in this conference.